So, yes, I will touch on deep learning techniques in general, but that is not the focus of today's talk. So, the focus of today's talk is on TensorFlow 2 versus PyTorch, the two most popular deep learning libraries. I'm going to talk about the pros and cons, why you should consider using one or the other. You can get the slides for today from my website, johnkrohn.com/talks. So when you go to that website, you will find a photo at the top of what the world was like when I could present at conferences in person, and then today's slides. You can just click and then you can download them in whatever format you want, PDF, PowerPoint, whatever. So yes. Drace, hello, what's going on? Drace is on. He knows my dog Obo, and he misses seeing Obo, evidently from the chat. Well, this is an illustration of my dog Obo by the wonderful artist Agle Bassins. Her artwork will be featured throughout this deck. So over the past few years, I've published 40 hours of videos and dozens of online trainings on deep learning, as well as lectured on deep learning at Columbia University and the NYC Data Science Academy, where I know Dre's from. Ultimately culminating in the release of this book, Deep Learning Illustrated, in November of last year. Across all of that deep learning education that I do, a single question is asked more than any of all of the others combined, and that is, so, TensorFlow or PyTorch? Given the popular demand, I couldn't resist dedicating my lecture to the topic today. Let's first do a couple of slides introducing deep learning for those among you who don't already know it. So this is MLconf. He works at Facebook alongside Igor, no doubt. They probably high five every day when there isn't a pandemic. Joshua Bengio, he's at the University of Montreal and runs a startup called Element.ai. And we've also got Jeff Hinton, who is a professor emeritus at the University of Toronto. And he runs the Google Brain team out of Canada. So what do these three men have in common? They are often called the godfathers of deep learning. And last year they were awarded the Turing Prize, which is the equivalent of the Nobel Prize in computer science, for their work on deep learning. So everyone's heard of deep learning. Probably a lot of you even know who these guys are, but I just love these illustrations of them. And it's these guys that we have to thank in bulk for a lot of the deep learning advancements that we have today. Let's start off by talking about an innovation of Jeff Hinton's from 2012. So here's an architecture that Alex Krizhevsky, Ilya Sutskever, and Jeff Hinton published on in 2012. It's named after the first author on that paper, Alex Krizhevsky, so it's called AlexNet. And AlexNet is what we call today a convolutional neural network architecture. You put in an image at one end, like an image of a cat, and then at the other end, it is trained to predict a particular label. So it might say, hey, there's a 99% chance this is a cat, there's a 1% chance it's a dog, and there's a 0% chance it's a horse or a flower. At each stage, at each layer of this deep learning network, there are artificial neurons, and these artificial neurons are designed to loosely mimic the way that biological neurons, biological brain cells work. And I've got here along the bottom snapshots of what the artificial neurons at each layer are specialized to detect. So here are each of the 96 artificial neurons in this first layer of the deep learning network. And what you can see is that each of these neurons is specialized to detect a straight line at a particular orientation, and that's it. So some of them detect vertical lines, some of them detect horizontal lines, others detect a 45-degree angle. They might do it between black and white or some other colors, but overall, the artificial neurons in this layer are specialized to detect straight lines at a particular orientation. The next layer can non-linearly recombine the information from the first layer, the representations from the first layer. So I have an example of 25 of the artificial neurons from this layer, and you can see that each one of them is specialized to detect a particular kind of curve or corner that's a nonlinear recombination of these straight lines. Then by the third layer, it can recombine the representations from the second layer, so we can have more complex curves and shapes. I've got 25 more artificial neurons displayed here. And by the fourth layer, these visual representations are very complex, very abstract, including neurons that are specialized to detect a dog's face, a cat's face, a clock face, and so on. So that's deep learning in a nutshell. That isn't the point of today's lecture, but I just wanted to make sure that we were all on the same page about what deep learning is before I dig into the main deep learning libraries. And in case it wasn't already clear from Igor's talk or from just your experience of machine learning in general, you should already know that deep learning has been a transformative approach in machine learning, including starting really in the modern times from that AlexNet architecture that I showed on the preceding slide. So in the ImageNet large-scale visual recognition competition, or let's just call it ILS-VRC for short, that competition was started in 2010, and you can see that in 2010, 2011, 2012, the vast majority of the models entered into the competition are what I call traditional machine learning approaches. I just use that as a term to mean non-deep learning approaches. So traditional ML could be regression models, support vector machines, random forests, and so on. So year over year from 2010 to 2011, we saw, okay, a marginal improvement in the top performing model. The error rate goes down slightly. And then in 2012, if AlexNet had not been entered into the competition, there actually would have been a modest worsening, a modest disimprovement year over year. But instead, Alex Krzyzewski, Jeff Hinton, and their team did enter AlexNet into the competition, and the error rate was reduced by a third year over year. Everybody was blown away, took notice. So across academia, across industry, all of a sudden, deep learning is something that people were interested in. And in the subsequent years, all of the top performing models were deep learning models. And just one really cool landmark here was passed in 2015, where deep learning models overtook human capacity on this image recognition task. Anyway, one last slide on deep learning. Just to explain why it's so powerful, why it was able to get those enormous gains over the traditional machine learning approaches. And that is that with the traditional machine learning approaches, we need to spend the vast majority of our time as an engineer working with those approaches, coming up with features that we can extract out of our raw data. So if we want to create a face detection algorithm, we need to become experts at the structure of faces and write algorithms to be able to predict where there might be eyes above cheeks. So the darkness of the eyes and the brightness of the cheeks, or the brightness of the nose with the darkness of the eyes on the other side. So we write functions to be able to extract these features out of the raw data. If you want to be a face expert, you're going to have to become an expert, or if you want to build expert face models, you're going to have to become an expert in faces. If you want to build a machine translation model, then you need to become a linguistics expert in the vast majority of cases with this traditional machine learning approach. So you spend a huge amount of your time becoming an expert in the particular type of data that you're working with and writing functions to extract features out of the data. And you spend a minority of your time actually designing and training models. With deep learning, this is turned on its head. And you might spend little or none of your time engineering features out of the raw data. Instead, you can rely, as we saw in AlexNet, on the layers of artificial neurons coming up with features, increasingly abstract, increasingly complex features that build on simple features in the first layer, in order to efficiently map whatever our input is, in this case pixels, to whatever our output is, in this case labels like cat or dog and what have you. So this deep learning approach means the feature engineering can happen fully automatically in a lot of cases. And instead, we spend our time designing and training these deep learning models, which can be a bit more labor intensive and is almost always more computationally intensive. And in a lot of cases, notwithstanding things like transfer learning and some other specialized cases, it likely involves larger data sets than you might have needed for the traditional machine learning approach. Anyway, so this lets you design state-of-the-art or approaching state-of-the-art face detection algorithms or approaching state-of-the-art machine translation algorithms without becoming an expert in face detection or linguistics, respectively. So it empowers all of us. And so now today we see deep learning everywhere in machine vision, like unlocking your phone. Any voice recognition algorithm today is going to use deep learning. Generative adversarial networks are a really cool technique for being able to take a sample data set and then generate new images in the style of that data set. So here are two made up celebrities. These people don't exist, but a GAN drew them based on a data set of high resolution celebrity photos that it was trained on. And deep learning also enables complex sequential decision making when applied into something called a reinforcement learning paradigm. So we can define a lot of board games, video games, self-driving cars, other applications where we have a series of sequential decisions as a reinforcement learning task. We can insert a deep learning algorithm into the model that we use to solve that reinforcement learning problem, and you can end up with things like an algorithm that can play the board game Go and defeat the world's best Go players, despite this being a highly computationally intensive and what players would consider to be an intuitive game. So that's deep learning in a nutshell. Given how powerful and transformative deep learning is, hundreds of software libraries have sprung up in recent years to make designing, testing, and deploying deep learning models easy. So here's a snapshot of the most popular libraries in deep learning today. So you can see TensorFlow in red has the clear lead. And then for a long time, we had the Keras library here in gold, which was, it still is today very popular, but it's been overtaken. Keras has been overtaken, and even TensorFlow, in terms of Google search frequency, could be overtaken soon by what we have in green here, which is PyTorch. So these three libraries, those are really the only three that you need to be aware of today. I'm probably going to insult some people in the audience with a comment like that, but these three libraries, TensorFlow, Keras, and PyTorch, are so much more wildly popular than any of the other libraries out there. In fourth and fifth place in terms of popularity are probably MXNet and Microsoft's CNTK library. And as you can see, these are left in the dust. Although, I wonder what would happen if I used Bing search results. That might give CNTK a little boost. I suspect that it's mostly used by Microsoft employees. So, all right. So these are the most popular libraries. As a kind of high level tour, I have more slides coming up with details on these libraries. The TensorFlow library was open sourced by Google. You can see there was a huge amount of popularity when they had a marketing splash when they first open sourced it and made it available publicly. It was derived from something called an internal project that they had called the dist belief project. And TensorFlow is the most popular library in production systems today. However, TensorFlow, particularly for its first few years, was relatively challenging to use. And so people came along, François Chollet in particular came along with the Keras library, which was originally designed for another library called Theano. But as Theano developers left the University of Montreal, where they were working on the Theano project, and got scooped up into higher paying roles at Google in Montreal, they began to, the Keras people began to allow their high level API for designing deep learning models to work on top of TensorFlow as well. And now today, the libraries work very close together. So the Keras API can be used for lots of different lower level deep learning computation libraries under the covers. However, it is primarily used with TensorFlow to the extent that the TensorFlow 2 release that happened in late 2019, it packages up Keras as a module within TensorFlow and recommends Keras as the primary tool to use to build your models, particularly if you're just getting started in deep learning. So that's TensorFlow and Keras. They are bedfellows. And then PyTorch, this is based on the Torch library, which I'll talk about a little bit more on the next slide. But it's a Facebook developer almost single-handedly ported that over the original Torch library into PyTorch, into Python. And it's a lot more Pythonic. It's easier to use relative to TensorFlow. And so it's really taken off. People love it. So just a little bit more data on TensorFlow and PyTorch. Now that I've kind of introduced to you that TensorFlow and Keras are, you can even think of them as the same in a lot of cases. They're not exactly the same, but they're used together so often you can kind of think of them as the same. So how popular are these two libraries in terms of job postings in the US? Well, you can see that TensorFlow has an edge, but PyTorch is close behind. So, regardless of the metro region, PyTorch is less popular, but approaching the popularity of TensorFlow. So on average, across all of these metro areas in the US, you can see that PyTorch is featured at 60% the rate of TensorFlow, with West Coast locations tending to outperform Northeast or Midwestern locations. But either way, 40 to 60%, 40 up to 80% of job postings mentioned PyTorch relative to TensorFlow. So in a bit more detail on these leading deep learning libraries, you'll notice first that I have a column here on Caffe, which used to be a very, very popular deep learning library. I venture to say that it's more popular today still than CNTK or MXNet, but I wasn't able to show it for you on that Google search results because a lot more people, many orders of magnitude more people search for coffee than they do deep learning libraries. So it kind of just blows out that whole chart. So Caffe, MXNet, and TensorFlow, they all have built-in Python implementations. They can all be called from Python. Torch, as it was originally written, was primarily designed to be called from Lua, which is a little bit of an obscure programming language, a little bit like JavaScript. However, now that it's been rewritten in PyTorch, that is the primary way that you would access the Torch library. And MXNet and TensorFlow have lots of other languages that are supported. TensorFlow, for example, has big projects supporting Python in C. It was originally designed in C++ before it was ported over to Python. And there's unofficial support in these libraries that I have in italics. So one of the major differences between these libraries for a long time was the programming style. So up until the TensorFlow 2 release late last year, TensorFlow was in the symbolic programming style like Caffe is. And this is it's a clever approach to programming, but it requires you to have many steps before you can even flow data through your algorithm and train your model. So you have a step where you design what your model should look like without putting any data in it. And then you have a second step where you take that design and you allocate it optimally across however many servers, however many CPUs, however many graphics processing units you have. And then finally, after you've done all that, you can start to actually flow information through your model and train it. So a clever approach, a highly optimal approach, but a more difficult approach to use. And so in recent years, the imperative programming style approach has really taken off. And that's what is a big part. It's a big part of what's allowed PyTorch to approach now TensorFlow's popularity. So this imperative programming style is what you're most used to. If you're in a Jupyter notebook and you create a variable, you assign a value to that variable, and then you add it to another variable, and you get the result in real time. That's the imperative programming approach. It doesn't require you to set up all the elements of the operation that you'd like to perform, allocate those elements across your devices, and then finally add values to them and allow the operation to happen. So this imperative approach is what we're used to. It's much easier. It's more interactive. A lot of people would say it's a lot more fun. I certainly would. And so the TensorFlow team has caught on to that. And since TensorFlow 2.0, TensorFlow has been imperative by default, though you can convert it into the old symbolic mode if you would like to. Now, all of these libraries allow you to parallelize your data across many GPUs, which allows training to happen a lot more quickly, obviously, by parallelizing. And all of them except Caffe allow you to even have different parts of your model split across different GPUs. All of these libraries provide you with access to large pre-trained models that you can fine-tune by transfer learning for some specific task that you have. Those are often called model zoos. And in terms of high-level APIs that make it easy to build deep learning models, MXNet is inbuilt. There aren't really other ways to go. It is by default a high-level, easy interface for designing deep learning models. TensorFlow has the Keras library, which of course I've already mentioned on preceding slides. And then I talked about the PyTorch. It's really not a high-level API. It's a complete rewrite of Torch, but it makes it easy to design your Torch models. Shiva.
Hi, John.
What's up?
Your time is up, but take a couple more minutes, and if there's questions, we should be taking it now. So please enter your questions into the chat box, and we can take care of those. And yeah, if you want to wrap it up, John, that would be great.
Wonderful. Any chance I can take a few extra minutes since my session started late?
Yeah, sure. Take it, especially because there's actually no session right after this. The next session, I believe, in this track starts at 11:35. So that's
Brilliant.
Fine with me.
Thank you so much, Shiva. And I will hang around. So I'll wrap up the talk in the next few minutes, and then I'll hang around any audience members that would like to through the break. I'd be happy to answer your questions then. So PyTorch, much better for interactivity. TensorFlow, much better for production deployments, which is really just the argument that I would make is that the only deep learning libraries you need to know are PyTorch or TensorFlow. So PyTorch, to summarize it in a single line, you can think of it as NumPy. It is super easy to use if you're used to numerical operations in Python, except that it's optimized for GPUs. So Py isn't. And also for automatic differentiation, which you need in order to train your machine learning models. TensorFlow, on the other hand, was ported to Python from C++, so it's clunky, a lot more difficult to use. It has much longer stack traces that are difficult to understand, whereas when you get an error in PyTorch, it's very easy to understand and typically resolved very quickly. PyTorch allows for dynamic auto-differentiation, so the size of your computational graph of your deep learning model can change with each round of training, with each batch of data that you throw at it, whereas TensorFlow, historically in TensorFlow 1, and today even in TensorFlow 2, assuming that you're using Keras to create your models, it has a static graph, meaning that all of your data, your inputs and your outputs have to be the same size. I already talked about the Keras API for TensorFlow. There is also a fast.ai API on top of PyTorch, which I think oversimplifies the deep learning process, gives you very little insight into what's happening under the covers. As I mentioned, debugging is easier in PyTorch. In contrast, TensorFlow is more widely adopted today, particularly in production systems. In terms of additional software, software that's available for these packages, the PyTorch library has the torch script just-in-time compilation, which allows PyTorch, even though it's now in this imperative programming style, it allows you to compile your code after you've designed it in the imperative style and allocate it efficiently across all the devices that you have. With TensorFlow 2, you have the same kind of thing, allowing that imperative to symbolic conversion. TensorFlow serving has lots of other libraries associated with it. TensorFlow serving for allowing you to train or deploy your TensorFlow model easily across lots of servers. The .js library for deploying your deep learning model right into someone's browser. The light library for allowing you to have it on a low energy device or a low compute device like a phone or a car, and the .data and .io libraries that allow you to have your data pre-processing and your input outputs all happen right there in the library. So PyTorch overall is more enjoyable for model design. TensorFlow is better for production deployments. In the next couple slides, I'll just give you a few examples of code in these two libraries, contrasting them. And you can see, and I'll use the fire symbol for PyTorch and water for TensorFlowing. So right from the get-go, you can see that even simple things like creating a tensor, in this case, a vector tensor, a one-dimensional array of numbers in PyTorch and TensorFlow, it's about it's the same level of difficulty to create them, but looking at the outputs, you get a much cleaner NumPy-like output in PyTorch, whereas in TensorFlow, you get this very long output. A lot of the information isn't information you're going to need regularly, and the information that you might most be looking for is kind of included there within a list. For more examples of kind of simple tensor structures, you can check out my Intro to Linear Algebra notebook at this GitHub repo of mine, ML Foundations repo. In terms of automatic differentiation, which allows us to calculate partial derivatives on our machine learning model in order to figure out how to adjust the parameters in the model to optimize them for some task, it is much, much easier in PyTorch. So if we want to do this simple operation for this equation y equals x squared, calculate the derivative of y with respect to x, and then find that derivative for some particular value of x, in this case 5. So the outcome is 10, and we get that answer in either library. But in PyTorch, it's much easier. It feels really straightforward. In TensorFlow, we need to wrap our operations within a with statement, and it's quite unintuitive. You can see more examples of this in the calculus notebook that I have at my ML Foundations repo. In terms of designing a neural network, here both libraries are effectively identical. And so you can see examples from my DeepNet and PyTorch notebook, my DeepNet and TensorFlow notebook, which are both available in my Deep Learning with TensorFlow and PyTorch GitHub repository. And then finally, for fitting models, in TensorFlow, assuming you're using the Keras module, it's a single line of code. In PyTorch, it's many more lines of code. And so this means that TensorFlow Keras for the novice deep learning practitioner is a little bit easier. It's actually a lot easier, particularly on this step. But once you get comfortable with deep learning, the PyTorch library allows you to have a lot more control. It allows you to have dynamic sized graphs that are changing with each batch of data and so on. And I've come over the years of using deep learning libraries to really love this PyTorch approach to training models. All right, so ultimately, at the beginning of this talk, I asked, should you pick TensorFlow or PyTorch? And the answer is both. So if you understand one, it's very easy to understand the other. If you're using deep learning professionally, you will run into both all the time anyway. You get a more granular perspective on model training in PyTorch, which makes it a little more complex than Keras, but also more flexible. PyTorch is more fun and easier to debug because the stack traces are straightforward. TensorFlow has a stronger open source ecosystem for distributed training and more flexible model options. So I do highly recommend learning both languages, and you can trivially translate between them using the Open Neural Network Exchange, or ONNX library. So if you're brand new to deep learning, I'd recommend starting with the TensorFlow library, particularly its Keras module, and then move to PyTorch once you're comfortable with the TensorFlow Keras approach. And then you can be creating your models, having a lot of fun doing that in Jupyter Notebooks and PyTorch. Use the ONNX library to train Flow perhaps for your production employments so that you can take advantage of all the serving, Init.js, light.io.data modules that TensorFlow offers. If you're brand new to deep learning, and you want to learn about the TensorFlow Keras approach or PyTorch, you can do exactly that by working through my book, Deep Learning Illustrated. So I have a special code here. You can access it at johnkrohn.com/ML20, all caps on the ML, and then use the code MLconf during checkout. That'll give you 40% off my books, as well as other books by my publisher Pearson in the machine learning space, and 60% off my videos. So please do stay in touch. I've got my email newsletter where I push out any new talks, any updates to my GitHub repositories. Have lots of content coming out on deep learning, but also the foundations of machine learning, linear algebra, calculus, probability statistics, lots of big course launches. If you're here today, I'd love to connect with you on LinkedIn to get to put a career and a face to your name in the chat. I absolutely love being connected with you folks on LinkedIn. I do have a YouTube channel where I publish lots of free videos on machine learning and deep learning in particular, and I tweet a bit as well. I also have a podcast, but I feel like I've now just talked way too much, and so I will turn it over to Shiva, who's very patiently waiting.